The ecologically relevant characteristics of flow regimes are fundamental inputs to eFlow's assessments, but detailed data on these characteristics are available only at gauging stations, which record flows in a small fraction of all reaches composing the world's rivers and streams. Moreover, the number of functioning gauging stations has declined in many countries over the past decades. Meanwhile, humans are altering flows in a large and increasing proportion of river reaches. So to be truly effective, eFlows need to be quantified and protected in all of these impacted reaches. Hydrologic classification provides a means of grouping data from available gauging stations into meaningful flow regime classes and then assigning ungauged river reaches to one of these classes. Let's have a look at the steps based on a framework published by Julian Olden and others. Hydrologic classification begins with defining the objectives of the classification. For purposes linked to eFlow's assessment, the objective will generally be to classify rivers according to similarities in ecologically relevant characteristics of their natural flow regimes. This level of classification requires information about detailed flow statistics like those coming from the indicators of hydrologic alteration method. This requires an inductive approach to classification that begins with detailed flow data, either from actual gauging stations or model outputs. The first step in the process is thus to acquire and evaluate the available hydrologic data. Detailed flow statistics will require data at a daily time step, and preferably from an extended period of time. In the classification of Australian rivers, Mark Kennard and colleagues began by acquiring data from 2,868 gauging stations with records longer than 10 years. They then screened these gauge records to select only those from 1. Rivers without significant alteration of the natural flow regime, 2. Records with 15 years or more data that include the year 1980 to ensure a degree of overlap, and 3. Continuous mean daily data where possible. The screening process reduced the original 2,868 gauging stations to the 830 stations plotted on the slide. Another consideration was the spatial coverage of gauging stations, which is acceptable. Few stations are present in the arid interior or outback of the country, but most of the other climate zones are well represented. The next step is to choose the metrics to be used and calculate them for each of the flow records. You'll remember that the indicators of hydrological alteration method includes 33 parameters to characterize annual variability in flow regimes and an additional 34 parameters to characterize 5 ecologically relevant environmental flow components. Other studies have identified more than 150 possible parameters, but many of these are redundant. Once the metrics have been calculated, it's necessary to screen them for outliers that may be due to data from rivers with altered flow regimes that slipped through the previous screening. Any gauging stations found to produce outliers can be removed from the analysis. It's also recommended to evaluate the uncertainty of metric values, which may be linked to different lengths or periods of gauge records. Metrics with high uncertainty values can also be eliminated if needed, while metrics with higher certainty can be weighted more heavily in subsequent classification steps. Finally, it's important to remove the scale dependence of flow magnitude metrics, which depend greatly on catchment area. Approaches include standardizing magnitude values by catchment areas or mean daily flow. Now, with your quality-checked metrics for a carefully selected range of gauging stations, you're ready to statistically analyze the metric variability across stations and group the results into a reasonable number of hydrologic classes. In the Australian example, they used a Bayesian mixture modeling approach. I refer you to the paper in the additional reading material folder if you'd like to delve more deeply into the details. The analysis resulted in 12 predicted flow regime classes, as shown on the slide. Environmental variables describing catchment topography and climate were also used in the assignment of gauge records to individual classes. Once the number and characteristics of classes have been determined from the gauging records, it's necessary to ascribe all river reaches to one of the classes. A number of approaches exist, including ordination and clustering approaches. Ordination approaches are useful in exploring continuous patterns of hydrologic variability among sites. Clustering approaches are what's most commonly applied. The results of the Australian example are shown on the slide. Note that the 12 classes chosen differ mainly in the degree of permanence of flow, being either perennial or intermittent, the stability of flow and seasonal variation in stability, and the predictability of flows. A large amount of additional information related to magnitude, timing of high flows, and other parameters are also more or less related to different hydrologic classes. Large-scale classification of hydrological regimes, coupled with knowledge that flow regime is a master variable in determining ecological integrity, enables e-flow scientists to also extrapolate flow ecology relationships more widely in river basins and regions. Ultimately, this enables extrapolation of e-flow's recommendations. We'll see applications of this as we go further in class. So what are the take-home messages from our quick look at hydrologic classification? First, hydrologic classification is essential to scaling up e-flow's information and prescribing environmental water allocations to whole regions simultaneously. And we learned that a clear framework for hydrologic classification includes steps to 1. Acquire and evaluate hydrologic data, 2. Compute hydrologic metrics, 3. Conduct the hydrologic classification, and 4. Ascribe all rivers and streams to the class. Please have a look at the reading materials both in the required as well as the additional reading folders to delve more deeply into this subject. That's the end of this lecture. Thank you.